All right. So 8.2 is taking matrices, and now we're looking at not so much as a system anymore. We're looking at it as operation. So we're going to be adding matrices. We're going to be multiplying matrices. We're going to be looking at it in different sense. We're also going to be looking at vectors and matrices. Okay. So a matrix can be denoted as an uppercase letter, such as like A, B, and C. So I'll just call matrix 1 A, like matrix 2 B, things like that. Okay. A matrix can be denoted by the representation element enclosed in brackets. Okay, such as A, IJ, comma B, IJ, or C, comma IJ. So those are your elements within that. Okay. So a matrix can be denoted by the rectangular array of numbers, such as A equals all of this, where we look at when you have A, 1, 1, that's just like the first entry. So it's row 1, column 1. A, 1, 2 is row 1, column 2. Okay. Things like that. Two matrices, A equals A, IJ, and B, IJ, are equal when they have the same dimensions, and IJ equals BJ. So element of A, row 1, column 1, is equal to row matrix B, row 1, column 1. So every element within it is equal to each other. Okay. So solve A11, A12, A21, and A22 in the matrix. Okay. So what it's just saying is these matrices are going to be equal to each other. So entry A, row 1, column 1 is equal to what? The second one? 2.
Yeah.
A, row 1, column 2 is equal to?
-1.
-1. A, row 2, column 1 is equal to?
-3.
-3. And A, row 2, column 2 is equal to?
0.
That's it. Okay. All right. So the definition of matrix addition, okay? The main thing is you can only add two matrices if they have the exact same dimensions, okay? So matrix A plus matrix B would be, first off, they have to have the same things, but to add them, we add the same elements. So we take A, row 1, column 2. Actually, we're using I and J, and we would add it to matrix B in the exact same location. Okay, so to add matrices, you add the exact elements to make a new one. Okay. All right. All right, so the sum of two matrices of different dimensions. So if we have a 3 by 3 and a 2 by 2, we cannot add those. So their sum is known as undefined. Okay, they're known as undefined. Okay. So let's look at a couple examples. Okay, in every single one of these, can I add?
Yes.
Yes, because every single one of these has the same exact dimensions. Okay, this one's a 2 by 2, and we're adding it by a 2 by 2. This one's a 2 by 3, and we're adding it to a 2 by 3. Okay, so as we add, again, we just add the exact same elements. So I'm going to take -1 and add it to 1, and that's going to go in the same position. So -1 plus 1 is 0. So that's going to be row 1, column 1. For the next one, row 1, column 2, I'm going to add 2 and 3, which is
5.
5. Row 2, column 1, 0 plus -1 is?
-1.
-1. And then row 2, column 2, 1 plus 2 is 3.
3.
And that would be the sum of those two matrices. Okay. All right, B. Now we're adding 0, 1, -2, 1, 2, 3 to the zero matrix. This is actually known as the zero matrix because every element is
0.
0. Okay. And when we add every element to the element of 0, isn't it going to be the exact same thing?
Yep.
So we're just going to end up with 0, 1,
Mhm.
-2, 1, 2, and 3. Okay. Go ahead and do C.
Easy.
So row 1, column 1, we get
0.
0. Row 2, column 1,
0.
0. Row 3, column 1.
0.
So when we added these, we actually got back to the zero
Zero
matrix.
matrix.
Yep, exactly. All right, any questions with that so far? Pretty straightforward?
Mhm.
All right, moving on. All right, scalar multiplication, okay? Scalar multiplication says if A equals the element of A row 1, column 1, is the M times N matrix, and C is the scalar, then the scalar multiple of A by C is this, okay, which is C times A. And all that means, guys, is you're going to take every element and multiply it by C. So if I'm taking 2 times, say this is 2, if I take 2 times the matrix of A, that just means I'm going to take 2 and multiply by every single element within my matrix. That's it. Okay. Negation. Does anyone know what negation means?
Negation.
Negation.
Isn't that to cancel out or something?
Kind of. It's actually the opposite. So the negation of A is just negative A. So it's the opposite of every single element. Opposite of every element. Okay. All right. For the matrices below, find A of 3 times A, then B, the negation of B, so the opposite of B, and then C, we're going to do 3 times A minus B. Okay. So if I'm looking at this for A, I'm taking 3 times A. So I'm going to take 3 and multiply it by every single element here. Okay. So 3 times 2 is
6.
6. 3 times 2 is
6 again.
3 times 4 is
12.
12. So that's the first row. Second row, 3 times negative 3.
Negative 9.
3 times 0.
0.
3 times negative 1.
Negative 3.
And then the last one, 3 times 2.
6.
3 times 1.
3.
And 3 times 2.
6.
And there you go. That is scalar multiplication. Okay. All right, B. We're taking the negation of B, so we're just taking the opposite of B. Okay, so the opposite of B. So the opposite of a positive 2 is?
Negative 2.
My 0 still stays 0, don't they?
Mm-hmm.
Okay, the opposite of 1?
Negative 1.
1. Opposite of negative 4?
4.
4. Opposite of 3?
Negative 3.
Opposite of negative 1?
1.
Opposite of 3?
Negative 3.
And the opposite of 2?
Negative 2.
And there you go. So there's B. Okay. Now, C, we can do it 2 different ways. Okay. So C, we could take 3 times A, which we already have, and then subtract off our B, right? Or subtraction means the same thing as adding its opposite, right?
Yes.
So 3A minus B is the same thing as 3A plus negative B, right?
Mm-hmm.
And didn't in A, we already do 3 times A?
Yep.
In B, didn't we already take its negation, its opposite? Yep. So now could we actually just add part A and part B?
Yes.
Yes, we can, because again, they're the same dimension, so we can always add them. So let's go ahead and do that. So 6 plus negative 2.
4.
4. 6 plus 0,
6,
12 plus 0.
12,
Okay, second row. -9 plus -1,
-10,
0 plus 4,
4,
-3 plus -3.
-6,
Yep. And the last one, 6 plus 1,
7,
3 plus -3,
0,
and 6 plus -2,
4.
4. And there you go. Again, it would have been the same thing if we subtracted. If we look at 3a minus, so if I did 6 minus b, so 6 minus 2 would have got me to 4. 6 minus 0 would have got me to 6. 12 minus 0 would have got me to 12. We would still got the same answer. I was just using what we did for part A and part B. But again, same thing. All right. Any questions with that? All right. Here are the properties of matrix, okay, of matrices. Okay. We're going to let A, B, and C be m times n matrices and let C and D be scalars. Okay. If we have A plus B, that's going to be equal to B plus A, right? That should make sense because if they're the same dimensions, does it matter the order you add those in?
No.
No. So this is really, isn't it the commutative property?
Yeah.
Yeah. Okay. And then in number 2, if I add B plus C first, then add A, isn't it the same as A plus B, then plus C?
Yes.
Because again, they have to be the same dimension, so you're adding the same elements in each one. What property is that? Do you guys remember?
No.
It's the associative.
Yeah, that's right.
Yeah. Okay. All right. If I take C times A or C times D first, then times A, wouldn't it be the same thing if I take D times A, then times C?
Yes.
Yeah. Again, that's just your associative property, but now it's of a multiplication, right? I times A equals A. What's I represent?
Identity.
Identity, right? The identity. And if you multiply anything by 1, right, isn't it back to itself?
Yes.
Yeah, so that's your identity property. Okay. If I have C on the outside of my scalar and I multiply it after I add A plus B, then multiply by C, isn't that the same thing as taking C times A plus C times B?
Yes.
Yep. What property is
Distributive.
that? Distributive. Yep. And then isn't D6 the same thing?
Yes.
So all the properties that we've learned with adding, subtracting, multiplying, or adding and multiplying, they're the same here too. Okay. Now-
Mrs. Cochran?
Yeah.
Nolan's texting me. He's trying to get in.
Oh, that's who that is. Okay. All right. Thank you for letting me know that because I'm not letting someone in. Hey, Nolan.
Your name's weird, Nolan.
Yes. I'm going to pause real quick. So we just went over like the properties in this sense, and it's the same thing with matrices and it is with like addition and multiplication. So addition is commutative, so it doesn't matter if I take matrix 1 plus matrix 2, it's going to be the same as matrix 2 plus matrix 1. And to add those matrices again, you just add the elements, the exact same place. So if it's row 1, column 1, you add that one to the other one. All right. So as we're looking at this one, okay, so practicing our addition, now we just have 4 matrices. Every single one of these has the same dimension because we have 3 rows by 1 column. Okay, so we can add all of these. And we just add their elements and we always end up with the same dimension here. Okay, so we'll end up with a 3 by 1. So 1 plus -1 plus 0 plus 2 is what?
2.
2. So that's going to go in my first column, or first row, first column. Second one, 2 plus -1 plus 1 plus -3 is?
-1.
-1. So that goes in row 2, column 1. And then our last one, -3 plus 2 plus 4 plus -2.
1.
Is 1. So there you go. That is your final matrix. Okay. So adding is going to be the exact same. All right. Now, example 5 here, we can do 2 different things. Okay. From our property says since these are both 2 by 2 matrices, we can add them, okay? So we could either do the parentheses first, where we add them first, then multiply by your scalar multiplication, or we could distribute that 3 to both of these, then add them. Does it matter?
No.
No, because they're equal to each other in that sense, okay? So I am going to add first. I like doing parentheses first, make it a little bit smaller in this sense. So I'm going to go ahead and add because these are the same dimensions. So -2 plus 4 is
2.
2. First row, second column, 0 plus -2 is
-2.
-2. 4 plus 3,
7.
and then 1 plus 7.
8.
8. Okay. So now we've added, now we have the scalar multiplication through it of 3. So we just multiply every element by 3. So 3 times 2 is
6.
6. 3 times -2,
-6.
3 times 7,
21.
and 3 times 8.
29. 24.
And there you go. So this would be my final answer. And again, we would have got the same thing if I multiplied everything by 3 first, then added the 2. Okay. Does that make sense to y'all?
Mhm.
Okay. All right. So Nolan, that's kind of what you missed at the beginning, but pretty straight. The only other thing that we talked about is if you see a negative B, that means the negation of B. And that just means take the opposite of every single element.
Okay.
Okay. So, all right, the zero matrix. Okay, the zero matrix actually is when every entry is
0.
0. Okay, so if you have a 2 by 2 would be every element, so there'd be 4 zeros. If it's a 3 by 3, you'd have 9 elements of zeros, right? If you have a 2 by 3, you would have 6 zeros in it. Just means every element is 0 in that. Okay. The additive identity, okay, the zero matrix is the additive identity. So the zero matrix is the additive identity. Why? Because think about the identity property. The identity property of addition says, if I add a number to 0, doesn't that get me back to its original problem?
Mhm.
Yeah, so identity means we get back to the original. So if I take any matrix, so A, and add it to the 0 matrix, won't that always get me back to its identity, the original matrix?
Yep.
Yep. Okay. All right, so solve for x in the equation of 3x plus A equals B. Okay. So what I'm going to do is I'm going to actually, without even worrying about the matrices real quick, let's go ahead and solve x as an equation first. Okay, so how would I solve for x first?
Put them A and B in.
Well, not even looking at this. How would I solve for x in this equation?
Oh, subtract A
Subtract
and then divide by
okay.
3.
3x equals b minus a, right?
Mhm.
And then technically, yes, you would divide by 3. But remember, when we deal with matrices, we can't multiply or divide by 3. We multiply by its
Scalar.
scalar, which is its reciprocal, right? So
Mhm.
can't multiply both sides by 1/3 instead.
Oh, yeah.
Yeah, so that would be x would equal 1/3 times matrix B minus matrix A. You guys okay with that?
Yep.
Now, could we go ahead and do this equation from these matrices?
Mhm.
Yeah. Orders of operation say I do the parentheses first. So can I subtract matrix B from matrix A?
Yes.
Yeah, so let's go ahead and do that. So let's do matrix B minus matrix A. So it's a 2 by 2. So we're going to end up with a 2 by 2. All right, so let's do the first row, first column, -3 minus 1.
-4.
-4. 4 minus a negative 2.
That's 2.
Try again.
Oh, minus negative 6.
6. Okay. Second row, first column, 2 minus 0.
2.
2. 1 minus 3.
Negative 2.
Negative 2. Okay, you guys okay with that? So this is the matrix of B minus A. Now we need to multiply it by what?
1/3.
1/3. So can I multiply now every element by 1/3?
Yep.
Yep. So what's negative 4 times a third? Isn't that just negative 4/3? Okay.
Yeah.
Yep. What's a third times 6?
That's 2. Isn't
2.
it? Yeah.
Yep. A third times 2?
That's 2/3.
2/3. And a third times negative 2?
Negative 2/3.
Negative 2/3. And there you go. So this is what x would equal. So if I take 3 times this matrix, add the A matrix, it should always equal what? B,
B.
right? That's what that equation says. If I take 3 times x, which is this equation or this matrix, plus my matrix A, I should end up with matrix B. So could you check that work if you wanted to?
Mm-hmm.
All right, any questions with that? Okay. Now, for us to add and subtract matrices, remember, they have to have the exact same dimension, okay? When we multiply matrices, they do not need to be the same dimension, okay? Now, here's the key thing that needs to happen, okay? So our first matrix, so let's just say matrix A, okay? If it's a 2 by 3 matrix, remember, row by column, right?
Mm-hmm.
To be able to multiply to matrix B, our column of the first one has to equal the row of the second one. Okay, so the column of the first has to equal the row of the second. So I know matrix B has to be a 3 by something matrix. And it doesn't matter. It could be a 3 by 2. It could be a 3 by 4. It could be a 3 by 10. But that column has to equal the row. So what I tend to do when I write this, let's do a 3 by 3. Okay. When I write a 2 by 3, 3 by 3, these two have to be the exact same. If they're the same, our final A times B would be a 2 by 3 matrix. Okay. So the column of the first has to be the same as the row of the second. Their result, their product will be the same row by the same column. Okay. And it'll make sense once we keep doing this here. Now, could I do B times A in this sense?
Yeah.
Okay, well, let's look. If I change that, B times A, my B was a 3 by 3, right? What is the dimension of my A? A 2
3
by
by
3, right?
2 by 3.
Is my row and column the same?
Oh, no.
No, so we could not multiply B times A. Matrix multiplication is not commutative. You cannot switch the order. Sometimes you can, but not always. Okay, so that's why I always like to write their matrices, their dimensions here, because if those middle two are not the same, you cannot multiply them. Okay,
Mm-hmm.
so let's look at this one, example 7. Find the product of A times B, if we can. Sometimes we can't. Okay, so what is my dimension of A?
It is 3 by 2 or 2 by 3.
It is a 3 by 2. You were right the first time. Why? Always rows by columns. Okay. What is the dimension of B?
2 by 2.
2 by 2. Okay. Can we multiply these?
Yes.
Yes, because these numbers are the same. My row and my column the same. Our product when we multiply A and B, it will end with a 3 by 2 matrix. Okay. All right. So how do we multiply these? Okay. So I'm going to go ahead and write this. So we know we have a 3 by 2 matrix. Okay. To get this first entry, okay, this is known as row 1, column 1, right?
Mhm.
So to get row 1 by column 1, I multiply the first row of my matrix by the first column of my second matrix. Okay, so I multiply the same entry and add them together. Okay, so I'm going to take a -1 times -3. What's a -1 times -3?
3.
3, yeah.
+3. And then I'm going to take 3 times -4, which is
-12.
-12. And then I add those numbers up. So what do I get? -9.
No, yeah.
Okay. All right. So now if I want row 1, column 2, I'm going to take row 1 and multiply it by column 2 and do the exact same thing. Okay. So I'm going to take -1 times 2, which is,
-2.
and add it to 3 times 1, which is,
3.
so -2 plus 3 is
1.
1. Okay. All right. Next one. Now we're in row 2, column 1, right? So I'm going to multiply row 2 by column 1. Okay. So 4 times -3 is
-12.
12, plus -2 times -4, which is
8.
8. And -12 plus 8 is
-4.
-4. Okay. Now for this spot here, we're in row 2, column 2. So I'm going to multiply row 2 by column 2. Okay. So 4 times 2 is
8.
8. Plus -2 times 1 is
-2.
-2. So what's 8 plus -2?
6.
All right. Now this one, we're in row 3, column what?
1.
1. So I'm going to multiply row 3 by column 1. So 5 times -3
-15.
plus 0 times -4.
0.
0. So we get -15. Okay. And then our last one, we're in row 2.
Easy.
So row 2, column
2.
2. So 5 times 2 is
10.
10 plus 0 times 1,
0.
which is 10. And this would be your final answer here. Not that bad. It's just more work. Really. Okay. All right. Now, could we have multiplied B times A in this problem?
No.
No. Again, because B is a 2 by 2 and A is a 3 by 2. They're not the same, right? And the reason being, because if we would go first row by first column, first row of B has 2 numbers. The column of A has 3. So we don't have enough units to multiply or entries that multiply each other. Okay. So we could not do B times A. Can't be done. Okay. All right. Let's look at example 8. Okay. Find the product of A times B. So what's dimensions of A?
A is 2 by 3.
2 by 3. Okay. What's B's dimension?
3 by 2.
3 by 2. Good. Can we multiply these?
Yes. You
Yes,
can also
we can.
multiply B times A.
And we can also multiply b times a, this one, yes. So this one is commutative. Now, what is my final answer going to be?
A
So a times
3.
b is going to be what dimension? What do you
2
think?
by 3.
It's close. It's going to be a 2 by 2. Why? Because the
Two.
3's are the same. It's always the outside.
Oh,
It'll be a 2 by 2. Okay. So let's go ahead and write our 2 by 2 matrix. All right. So a times b. So we go row times column. Row times column. So now we have 3 numbers to multiply and add, right? So this
Mhm.
first entry. So we're going to take 1 times -2. -2. Plus 0 times 1 is 0.
0.
Plus 3 times -1,
-3.
-3. So what do I end
-5.
up getting for that one?
-5.
-5. Good. All right. Second entry here. So row 1, column 2. So row 1, column 2 now. So 1 times 4,
Well, 4.
4. 0 times 0,
0.
0. 3 times 1,
3.
3. So we
7.
get 7. Good. Okay. Row 2, column 1, right? This is row 2, column 1. So we multiply row 1, row 2, column 1. Okay. So 2 times -2,
-4.
-4. Plus -1 times 1,
-1.
-2 times -2.
2. -3.
So -3. All right. The last one, row 2, column 2. So wherever this entry is what we have to multiply. Row 2, column 2. So 2 times 4,
8.
-1 times 0,
0.
and -2 times 1.
-2. 6.
So we get 6. And there you go. That's your a times b. Okay. Any questions with that? Okay. All right. Example 10. Find a squared. What does a squared mean?
A times
Oh, wait,
itself.
you would just multiply it by itself.
Yeah, a times a. So here's a. Can I multiply it again by a?
Yep.
Yeah, because what dimension is a?
2 by 2.
By 2. So the middles are the same, right? Our row and columns. So what will we end up with when we multiply?
2 by 2.
A 2 by 2. Okay, so we're going to end up the 2 by 2. So first entry, row 1, column 1. So row 1, column 1. So 3 times 3
9.
plus 1 times -1.
-1.
So we get
8.
8. Row 1, column 2. So row 1, column 2. 3 times 1
3.
plus 1 times 2.
2. 5.
So we get 5. Good. Next one, row 2, column 1. Row 2, column 1. -1 times 3
-3.
plus 2 times -1.
-2.
So we get -5.
5.
All right, last one. Row 2, column 2. Row 2, column 2. So -1 and 1.
-1.
2 times 2.
4.
And we
3.
get 3. And there's a squared. Okay. And if you can't multiply, you just say not multiplied. Okay. Undefined. You can't multiply those together. Okay. All right.
That's funny.
What?
I was looking at the answer for that last one. If you look at it, 8 minus 5 equals 3. 3 plus 5 equals 8.
Yep.
I just realized that.
All right. So properties of matrix multiplication. same idea in that sense. I'm not going to go through all of those. Okay. Identity matrix. Okay. Identity matrix, when you're looking at dimensions in that sense, it's just denoted n times n. They should always be the same. Okay. Nothing crazy there. So we're going to use matrices to transform vectors. And did you guys do vectors in algebra 2?
I don't remember.
You don't remember. Okay. The vector is just, remember, from our coordinate plane. If I have the vector 2, 4, it's just over 2 up 4. The vector is just a coordinate, and then it's the segment from 0, 0 to that point. Okay. And then V in this case was 6, 2. Okay. So if I went over 6 up 2, or somewhere over there, okay, we would have that. Use a matrix to find each vector. Okay. In this sense, guys, don't make it complicated for it. If we have a vector V of 2, 4, 4, we can put it as a matrix of just a 2 over 4. So a 2 by 1 matrix. Okay. So if we have vector 2, 4, it's just the matrix of 2 over 4. Okay. So then W in this sense would be what? 6 over 2, right?
Yeah.
So they are 2 by 1 matrix, right? Both of them. Okay. So their vectors make a 2 by 1. Now from this, could we find V plus W?
Yeah.
Yeah. So we can add these because they're the same dimension. So V plus W would be what? 8 over
6.
8 over 6. So the vector of V plus W would just be 8, 6. Okay. And then for part B, would we be able to do W minus 2V?
Mm-hmm.
Yeah, what does that 2V mean?
2 times V.
2 times V, right? And if V is 2, 4, what is 2 times V? 4 over 8, right? And then can I subtract that from W?
Mm-hmm.
Oops, I don't know, I put a fraction bar there that shouldn't be there. So what is 6, 2 minus 4, 8? 2 over -6, because 6 minus 4 is 2. 2 minus 8 is -6. So that would be the vector of 2, -6. Okay. All right. Find the product of A times vector V. Okay. Do you think you guys can do that? So what's my A? My A is 1, 0, 0, -1. V is the vector of 1, 3, right?
Mm-hmm.
Can we multiply these two?
Mm,
Well, let's see. What's the dimension of A?
2 times 2.
By
2 by
2.
2.
And vector V is a
2 by 1.
2 by 1. So can I multiply those?
Yeah.
Yes. And they're going to end up as a what?
2 by 1.
2 by 1 matrix. So it's going to be a 2 by 1. Okay. All right. So let's go. Row 1, column 1, right? Which is the spot. I don't know why I put that really high. 1 times 1 is 1 plus 0 times 3 is
0.
0. Okay. So 1 plus 1 is, and I kind of wrote that weird, but 1, right? 2 by 1. I kind of put these, there you go. All right, next one. Row 2, column 1, right? So 0 times 0 is 0,
0.
plus -1 plus 3 is, or -1 times 3 is
-3.
-3, and 0 plus -3 is?
-3.
So A times vector V is the vector of 1, -3. Alrighty, any questions with that so far?
No.
Alrighty, good. Now, let's do some application ones. Your guys' favorite, the story problems. All right. So for the system of linear equations, write the system as a matrix of A times X equals B, and then B, use Gauss-Jordan elimination on A to B and solve the matrix X. So we're just finding what X, kind of like X, Y, and Z are, okay? And remember when we use Gauss-Jordan, it was ones in the diagonal and zeros everywhere else. That's where we did that row, reduced row echelon, where we had zeros above it, zeros below it, and the ones in the diagonals, okay? So if we want to write this as a matrix equation of A times X equals B, okay? A is just our matrix, taking this into our matrix form, okay? And this is, when we look at this, A is always just the coefficients. X are the variables we try to solve. And then B is my solution, okay? Which is the what X or what it equals, each equation, okay? So if I look at the first one, let's go ahead and just do A, our coefficient. So this is A here. So 1, -2, 1. B, our second equation, 0, 1, 2. And third equation is 2, 3, -2. Is everyone okay with that?
Mm-hmm.
Okay. Now, if we're multiplying, right, if this is a 3 by 3, we know X has to be a, if this is a 3 by 3, we know my X has to be a 3 by something, right?
Mm-hmm.
Okay. And actually, how many missing variables do we have? We have 3, so it's going to be a 3 by 1. Sorry, 3 by 1. Okay. All right. So we have X1 we're trying to find, X2, and X3. Okay. And then B is my answer, which is a -4, 4, and 2. Okay. Since this is a 3 by 3, my answers was a 3 by 1. We know our variables, we have 3 missing. It has to be have 3, and we have 1 row to that. Okay. Or 1 column, excuse me. Okay. So that's just A, writing it as a matrix equation. Okay. Now, let's go ahead and do what we did on last class, okay, where we went ahead and just made it as an augmented matrix, okay, where we don't have the X1, the X2s, the X3s, okay? So let's look at our augmented matrix, okay? And that's where we had our coefficients, so the 1, -2, 1, and then we put ... remember -4. Then we had 0, 1, 2 equals 4, and then we have 2, 3, -2, 2. Okay. All right. So now we want to write this into, use Gauss-Jordan elimination. So we want ones in my diagonals, right? And we want zeros everywhere else. You guys okay with that?
Mm-hmm.
Okay. So the nice thing is we have our ones in the first two. We have a 0 here already. We just need a 0 in this spot here. So let's start here. How could I get this to be 0?
Multiply by 0.
I could, if I multiply by 0, doesn't that cancel everything out in the bottom? Think of elimination. Okay, think of elimination. If I want this to be 0, I would have to add it with one of the equations.
Oh, -1.
Well,
So
this
times it
this
by
would have to be a
-1/2.
-2, that first equation, right?
Mm-hmm. Times it by -1/2.
How about
Right.
-2? I'm going to multiply the first equation by -2 and then add it to the third one. Okay. Why? Because remember, JD, when we were doing elimination before, we wanted to match the coefficients up.
Mm-hmm.
So to match the coefficients up, if this is 2, wouldn't I need -2 to be able to add the equations to eliminate it?
Oh, yeah.
That's what we're doing in this case, okay? When we
Oh.
get to 0, it's just like eliminating that variable.
Oh, okay.
Okay. And I know you weren't here last class, that's why it kind of, we had a, yeah. So I'm going to rewrite my first one. So 1, -2, 1, -4, 0, 1, 2, 4. Okay. All right. So now the last one, -2 times 1 is -2. -2 plus 2 is 0. -2 times -2 is -4, or excuse me, +4. +4 plus 3 is
Is 1.
po-
Or plus 3, you said? 7.
Yeah. so +4 plus 3 would be 7, right?
Yeah.
Okay. -2 times 1 is -2. -2 plus -2 is -4. -2 times -4 is 8. 8 plus 2 is 10. Okay. You guys okay with that?
Mm-hmm.
Okay. So now the next one. Okay. Now we have ones here and we have zeros here, which is great. So we need to get a 0 here and a 0 here. Okay. So if I need a 0 here, what could I do to the second equation to get to a 0 to -2 to be a 0?
Multiplied by 2.
Multiply by 2. So I'm going to multiply the second row by 2 and add it to the first row. You guys okay with that? Sorry, that should go there. So the second row is going to stay the same for a second. Okay. All right, so 2 times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. 2 plus -2 is 0. 2 times 2 is 4. 4 plus 1 is 5. 2 times 4 is 8. 8 plus -4 is 4. All right. Now, let's go ahead and work on the bottom one here too. To get this to be 7, wouldn't I have to multiply the second row by -7?
Mm-hmm.
So I'm going to multiply the second row by -7 and add it to the third row. Okay. So -7 times 0 is 0, plus 0 is 0. -7 times 1 is -7, plus 7 is 0. -7 times 2 is -14. -14 plus 4 is, sorry, -14 plus -4 is -18. -7 times 4 is -28. And what's -28 plus
Negative
10?
18.
-18. Okay. All right, you guys okay with that?
Mm-hmm.
All right. Now, last thing is we need to get this to be 1, right? That to be
Easy.
1, and then the other ones to be 0 above it. If I want this to be 1, couldn't I just multiply the last one by -1/18?
Mm-hmm.
Yeah. So I'm going to go ahead and just multiply the last row by -1/18. I'm going to rewrite my first ones for a second. All right. So -1/18 times -1/18 is 1 equals 1. You guys okay with that?
Yeah.
All right. Now we need to get this to be 0 and this to be 0. Can we do that? Yeah. Because to get 2 to be 0, wouldn't I have to multiply the third one by -2 and add it to the second row?
Mm-hmm.
Yeah. So let's go ahead and do that. So -2 times 0, 0 plus 0 is 0. -2 times 0 is 0, plus 1 is 1. -2 times 1 is -2, plus 2 is 0. -2 times 4, -2 times 1 is -2, plus 4 is 2, right?
Mhm.
2, okay. And then to get the last row, I want this to be 5, right? Right now this is 5, so this one would have to be a -5. So now I'm going to multiply -5 by the third row and add it to the first row. So -5 times 0 is 0, plus 1 is 1. -5 times 0 is 0, plus 0 is 0. -5 times 1 is -5, plus 5 is 0. -5 times 1 is -5, plus 4 is -1. Okay. Now, why did I do all of this? Because if everything's 0 and these are 1s, this, remember, is my X1, this is my X2, this is my X3, and these are my solutions. So we know X, which was the matrix of X1, X2, X3, doesn't that just equal -1, 2, and 1?
Mhm.
Yeah. So this says X3 equals 1, X2 equals 2, and X1 equals -1. There you go. Any questions with that? All right. So this kind of reviewed, which helped you, JD, since you weren't here, trying to get to that reduced row echelon form. And that
Yep.
helped you find what your actual Y and your Z are, or W in the original case. Okay. All right. Example 14. 2 softball teams submit equipment lists to their sponsors. So here's the equipment for women's team. We need 12 bats, 45 balls, and 15 gloves. The men's team, 15 bats, 38 balls, and 17 gloves. Each bat costs $80. Each ball costs $4, and each glove costs $90. Use matrices to find the total cost of our equipment. Okay. Well, let's think about this. If honestly, I probably wouldn't do a matrix for this, because if you buy 12 bats for $80, you would just do what? 12 times 80 to get a total cost, right?
Yeah.
But we're going to go ahead and do it in this matrix form here for a second. Okay. So we know, let's do our equipment matrix. Okay. So we have a women's team and we have a men's team. So let's put women's first and then men's second. So women's, we know we need 12 bats, 45 balls, and 15 gloves. For the men's, we need 15, 38, and 17, right? So this will be bats, balls, and gloves. Okay, you guys okay with that?
Mhm.
Now, we know a cost for each of these, right? We know the cost for the bat is $80. We know the balls cost $4 and a glove cost $90. Okay. Now, the reason why I wrote it horizontally here is because think this is a 3 by 2, right? This one is a 1 by 3, right?
Yeah.
Okay. The only way we can be able, because if we're trying to find a total cost, don't you take equipment times cost to get a total cost? We need to
Mhm.
multiply these matrices, correct?
Yeah.
Okay. Now, to be able to multiply these, if this is a 3 by 2 and this is a 1 by 3, I can't do equipment times cost, can I? But could I
No.
do cost times my equipment?
Yeah.
Yeah, because my cost is a 1 by 3 and my equipment is a 3 by 2. So now can I multiply them?
Mhm.
Yes, because they're both 3s. And what would we end up getting? A 1 by
3
a 1 by
or 2.
1 by 2. Okay. So let's take cost times equipment, and we're going to get a 1 by 2. So 1 row, 2 columns. Okay. So let's do this. We're doing cost times equipment. So cost, so row by column. So we're going to take 80 times 12 plus 4 times 45 plus 90 times 15. Are you guys okay with that?
Mhm.
And that will be that first row, first column. For the second one, and we'll do that math here in a second. Okay, the second one, this is row 1, column 2. So I'm going to take 80 times 15 plus 4 times 38 plus 90 times 17. Okay, and now let's do the math. So the first one, in the blue, we get 2,490. And the second one, we get 2,882. So we know it's going to cost the women's team how much money? What do you think? Is the women's the 2490 or the 2882? What do you think?
2882. All right.
2490.
2490.
2490. Why is it the 2490?
Because it's the first column.
It's the first column. It's the first column. Was women's. So then the men's team would cost us 2882. And there you go. Okay. Now, personally, on this problem, I probably wouldn't have used a matrix. I probably would have just known I'm going to take 80 times 12, 4 times 45, 90 times 15, and just add them up. Okay. But using matrices, that's what they are for, that you can do that. Okay. That is actually 8.2. Is there any questions on any?